Incredibly happy, researchers around the globe marked the beginning of the operation of the largest and strongest high-energy particle collider ever built. They finally got to witness how this amazing creation altered our understanding of the cosmos, and it was worth the wait of several decades. The Large Hadron Collider at the European Organization for Nuclear Research finally began running in September 2008 after a very protracted building period. The Large Hadron Collider took years to develop, but it has many experimental runs that have led to the solution of many cosmological mysteries. CERN scientists recently stated that when they increased the energy of the beam passing through the Large Hadron Collider to its maximum possible, they witnessed something odd and alarming. In this video, we'll be talking about the new discovery made by CERN. Stay with us till the end of the video to know exciting information. An accelerator of particles with the highest power in the world. The Large Hadron Collider is the world's most massive and powerful particle accelerator. You can find it in Switzerland at the European Laboratory for Particle Physics. After being shut down for 3 years for repairs and maintenance, the Large Hadron Collider resumed operations on April 22, 2022. Run 3 is scheduled to begin exactly 1 day after the 10-year anniversary of the Higgs boson's discovery. At the Large Hadron Collider, a particle physics lab, scientists have put the Standard Model's predictions to the test. There are aspects of particle physics that cannot be explained by the Standard Model. For example, both dark energy and dark matter have their own mysterious characteristics. If you're wondering why the matter is so much more common than antimatter, this may be worth considering. The Large Hadron Collider was created to help achieve this aim. The massive accelerator provides a safe and regulated environment for the collision and analysis of subatomic particles at very high energies. With the discovery of the Higgs boson in 2012, the Large Hadron Collider achieved one of its greatest successes to date. The European Organization for Nuclear Research is responsible for the discovery of a number of previously undiscovered subatomic particles. News of the discovery of X particles within the quark-gluon plasma, produced at the Large Hadron Collider, was announced in January 2022. To use technical language, scientists at CERN had recreated circumstances last seen in nature shortly after the Big Bang. It's about to get very interesting in terms of learning about the Large Hadron Collider and CERN, as Run 3 is set to start and a flurry of discoveries is on the horizon. The enigmatic properties of elements. Particle accelerators like CERN's Large Hadron Collider speed up particles to extremely high velocities in a controlled manner in order to explore their interactions at the subatomic level. With a diameter of over 17 miles, the Large Hadron Collider is the world's largest particle accelerator. The H in the center of the word Hadron, which is also the symbol for the Large Hadron Collider, represents composite LHC, particles consisting of smaller elementary particles called quarks, such as protons. When two beams of particles traveling in opposite directions collide and are accelerated, the LHC produces spectacular effects. Physicists, contrary to common assumption, are eager to find gaps in the Standard Model in order to begin to account for the enigmatic properties of elements like dark matter and dark energy. The supporting components of Large Hadron Collider. The Large Hadron Collider's primary machinery would be useless without its supporting components. According to a CERN LHC publication, the primary accelerator is preceded by a succession of smaller accelerators that gradually increase the particle's speed. The last link in the chain, the superproton synchrotron, has a radius of nearly 4.3 miles. Thus, smaller is a similar term. CERN claims these results in two beams, moving in opposing directions at the speed of light that circumnavigate the LHC. A powerful magnetic field keeps the beams circulating by redirecting the direction of electrically charged particles. All of the exciting research conducted at the LHC was made possible by bringing together and colliding opposing beams at 4 different points along the Large Hadron Collider enormous ring. When two particles collide with this much power and speed, they create a deluge of brand new particles, the majority of which have vanishingly short lifetimes. However, scientists have challenges when trying to determine the nature of these particles. Modern particle detectors at the Large Hadron Collider include an array of specialized units, each of which is designed to collect data on a particular type of particle or to measure a certain property of particles. It is possible to determine the electric charge and momentum of a particle by observing its curving route through a magnetic field, and this can be done with a calorimeter. There are 4 potential collision sites in the vicinity of the Large Hadron Collider. However, Two of them are now being utilized by massive general-purpose detectors. The compact muon solenoid is a device like a gigantic 3D camera that snaps 40 million images each second of particles. Inside the detector, a giant magnet called a solenoid directs particles along their prescribed paths. While it may have a cutesy moniker, this detector actually packs quite a punch at 12,500 tones. Muon, the particle described by the middle term, is nebulous in nature, resembling an electron but being significantly more massive, and its detection requires a complicated array of subdetectors coiled around a solenoid. The other general-purpose detector at the LHC is called ATLAS, and it works similarly to CMS, except that it uses a different detection, subsystems, and magnets design. In spite of being the largest particle detector ever built, its spatial efficiency is inferior to that of the compact muon Soleil. Impacts of lead ions in a lab setting. On Friday, November 18, 2022, collisions of lead ions were used to test the new detectors and data processing systems in preparation for the forthcoming lead physics experiment at the Large Hadron Collider. Lead nuclei returned to the LHC on Friday after a 4-year hiatus, after the formal commencement of Run 3 in July, which comprised proton collisions just at a record energy of 13.6 T electron volt. Quark-gluon plasma is a form of the matter investigated at the LHC in which the fundamental constituents, quarks and gluons, were free to move and interact over a much larger volume than usual. Lead nuclei with their total of 208 protons and neutrons are used for this purpose. On Friday, scientists collided with lead nuclei at a record-setting 5.36 T electron volt per nucleon, an important milestone on the road to the lead collision scheduled for the 2023 Run 3 and Run 4 physics runs. When two lead nuclei collide head-on, each of their 208 nucleons can potentially interact with several nucleons in the other nucleus. Increase in lead ion ray intensity. The high luminosity LHC will double the lead ion beam intensity, calling for several upgrades to the current CERN ion injector complex. To do this, the super proton synchrotron employs a technique known as momentum slip stacking, in which 8 lead ion bunches are slipped from 2 batches separated by 100 nanoseconds. So we can increase the maximum number of bunches injected into the LIHC from 648 in Run 2 to 1248 in Run 3 and beyond. Once the modifications are finished, it will produce 10 times as many heavy ion collisions as in prior run. The ALICE LHC experiment, which investigates lead ion collisions, also made a substantial advancement with this trial. During the recent LHC downtime, the ALICE collaboration was able to add numerous new or significantly improved detectors, as well as updated equipment and software for data processing. The enhanced detectors allow for a finer level of detail to be reconstructed when tracing the paths and characteristics of particles created in collisions. Furthermore, the whole collision can be recorded by the advanced equipment and processing chain. Lead-on lead collisions produce record-breaking energy. The test run was also utilized by other experiments to commission their updated and newly installed subsystems for use in the new heavy ion environment of higher energy and 50 nanosecond bunch spacing. With the improved selection program, ATLAS will be able to obtain more accurate data on heavy ion physics during Run 3. The goal of the testing of this novel particle track trigger is to increase the number of ultra-peripheral collisions that may be detected, to take full advantage of the high-energy lead collisions. CMS has upgraded its readout, data collecting, trigger, and reconstruction chains. With LHC lead fills, CMEDS was able to activate its full beam line in preparation for heavy ion operations in 2023, allowing for the identification of areas for further optimization. With the emergence of lead-lead collisions, which are notorious for their unusually high particle multiplicity, the commissioning of a new Large Hadron Collider B detector commenced. LHCb has been able to collect data from lead and lead-argon collisions during fixed target mode thanks to the new SMOG-2 device, which is designed to introduce noble gases into the collision area. The 2022 lead program for the Large Hadron Collider Accelerator, the tests, and CERN's Heavy Ion Injector Complex were finished in 2021 and were a success despite its brevity. The 4 major Large Hadron Collider detectors have recorded new maximum energy for lead collisions. The scientific community is eagerly anticipating the commencement of a heavy ion physics campaign in 2023 or beyond. That's all for today. Thank you for watching. If you enjoyed the video, do like and subscribe to this channel.